Welcome to Naradar Academy. In this video, we are going to discuss how to check whether a given polynomial is reducible or irreducible. Okay, so first let's start with a few definitions. The polynomial f of x equal to a0 plus a1x plus etc. up to an x power n, where this a0, a1, etc. an are integers, is said to be primitive polynomial if GCD of all the coefficients is equal to 1. So primitive means what you have to do, you take all the coefficients a0, a1, etc. up to an, you find the GCD. If the GCD is equal to 1, the polynomial is said to be a primitive polynomial. If you take two primitive polynomials f of x and g of x, then their product f of x into g of x is also a primitive polynomial. Then next one, suppose if my polynomial is not primitive, that means what? The GCD is not equal to 1, right? So if it is so, then that number, that GCD is called content of the polynomial. Okay, see, the content of the polynomial is defined to be GCD of a0, a1, a2, etc. up to an, right? If D is the content, then f of x can be written as D into g of x, where D is the content and g of x is a primitive polynomial. Obviously, for a primitive polynomial, the content is equal to what? 1. But we don't define content for primitive polynomial, we define it for only non-primitive polynomials, right? Next one, a polynomial is said to be integer monic if all its coefficients are integers and highest coefficient is 1. Here highest coefficient means, I mean the coefficient of the highest degree, right? So when will you say a polynomial is monic? When the coefficient of the highest degree is equal to 1, right? All integer monic polynomials are primitive. Why I am saying like this? Because see, monic means what? Highest coefficient is equal to 1. No, if any one of the coefficient is 1, then GCD will be obviously equal to 1. Therefore, it will be obviously a primitive polynomial. Therefore, integer monic polynomial means it will be primitive. You note the point that here I have described integer monic. If it is not integer monic, if it is defined over the rational numbers, it need not be primitive, because rational number means you will be having fractions also, right? So there the case may be different, right? Okay, now let's see some examples. Look at this polynomial, x power 5 plus 5 x power 4 plus 3 x square plus 2 equal to 0. Here see, the coefficient of the highest degree is what? X power 5. So here the coefficient is 1. Therefore this is called monic polynomial, integer monic polynomial. And this is also primitive, because if you take the GCD of the coefficients, what are the coefficients here? 1, 5, 3, 2. GCD of all these coefficients is equal to 1, no? So it is primitive. So this is integer monic as well as primitive polynomial. Next consider this one, 10 x square plus, sorry, let it be like 10 x cube or something, right? Let 10 x cube plus 5 x square plus 3 equal to 0. This is what? This is only primitive, but it is not integer monic, because here the highest degree is 3 and its coefficient is 10. Therefore this is not monic polynomial, but it is primitive, because if you take GCD of 10, 5 and 3, GCD is equal to what? GCD of all the three coefficients equal to 1. Therefore this is a primitive polynomial. Next consider this one, 2x square plus 8x plus 4 equal to 0, right? This is not monic polynomial, because the coefficient of x square is not equal to 1. Therefore this is not monic, and this is not primitive also, because GCD of 2, 8, 4 is equal to what? 2 only, no? Therefore this is not primitive. And the content of this polynomial equal to 2. What is content? Content is nothing but GCD of the coefficients, right? So these are the preliminary things about polynomials. Now, in order to check whether a given polynomial is reducible or irreducible, we have a important theorem which is known as Einstein's criterion, with which we are going to check whether a given polynomial is reducible or irreducible. Before that, what do you mean by a reducible polynomial? Suppose if a polynomial is given, then if it can be written as product of some factors whose degrees are less than the given polynomial, then it is said to be reducible. Okay, otherwise it is said to be irreducible, right? Now let's see what is Einstein's criterion. Let us take one polynomial of nth degree with integer coefficients. Suppose we have a prime number p. Okay, we have a prime number p such that this prime number divides a0, a1, a2, etc. an minus 1. That is, this prime number divides all the coefficients except the nth term. Okay, an. P does not divide an. Also, p square does not divide a0. In this case, the given polynomial is irreducible over the rational field. Okay, right? This is called Einstein's criterion. Then one more result for checking the reducibility of a polynomial. Let f of x equal to x power n, a n minus 1, x power n minus 1 plus etc. up to a naught be a monic polynomial. See here, I have taken monic polynomial, that is the coefficient of the highest degree is equal to 1, right, with integer coefficients, and a naught is not equal to 0. The constant term should be a non-zero value. Okay, so if these conditions are satisfied, suppose if this polynomial has factor in the rational numbers, then it also has a factor in integers. Okay, whenever a polynomial has a factor or has a root in the field of rational numbers, definitely it will have a factor in z, right? And this m, this integer m is there, no, that will divide a naught. That will divide a naught. Okay, so what do we say here? If we take a monic polynomial, suppose if it has a factor in q, definitely it will have a factor in z also, and the corresponding factor in the integers will divide this constant term. Okay, while looking at the examples, you can understand this type easily. So this is another result for checking the reducibility of a polynomial. Next one is cyclotomic polynomial. X power p minus 1 by x minus 1, which is equal to x power p minus 1 plus x power p minus 2 plus etc. plus x plus 1 is irreducible over q. Okay, irreducible over q for any prime number. This result is true. So if a polynomial is given like this, 1 plus etc. x power p minus 1, then you can directly write it is irreducible over q, right? Next one is, if p is a prime number and we have a polynomial f of x over integers with the degree of f of x is greater than or equal to 1. Now let us define a new polynomial f bar of x in z p of x. See, the given polynomial, original polynomial is given over integers. Now I am defining a new polynomial from this in zp of x. Zp we know, no? Yes, modulo group, right? Now here, how I getting this f bar? In f, no, you have the coefficients, no, rewrite all the coefficients as modulo p, only the coefficients, not the powers of x, right? After rewriting this, you check whether f bar is irreducible in zp. If it is irreducible in zp, then f of x is irreducible over q. Okay, certain things has to be kept in mind while using this problem, while using this result for problems. The first one is, you are transforming, no, that is you are transforming the polynomial from z of x to zp of x. While transforming that one, you have to keep in mind the degree of both the polynomials should be equal. The degree should never get reduced. This is the first thing you have to keep in mind. Then another one is, at least for one prime number it must be irreducible. This result you can use only for irreducible polynomials. Okay, if for at least one prime number f bar is irreducible, then f is irreducible. Suppose if you are taking one prime number and in that zp of x, if that polynomial is reducible, you cannot come to a conclusion that it is reducible over q. Okay, this result is true only when the polynomial is irreducible. Okay, while doing the problem I will explain you more about this result. Okay, right. Then next one is, for any prime number p, x power p minus 1 minus 1 can be factored into x minus 1, x minus 2, etc. x minus p minus 1 zp of x. Okay, next, If x and y belong to integral domain of prime characteristic p, then x plus y power p equal to x power p plus y power p, and similarly x plus y power p power n equal to x power p power n plus y power p power n. So now let's see some examples. Okay, now you consider this polynomial x power 4 plus 4 in z5 of x. We have to check whether this is reducible or not in z5 of x. z5 contains only the coefficients from 0, 1, 2, 3, 4, isn't it? Right. Now f of x equal to x power 4 plus 4. Whenever you are given with sets like this, that is z5 of x, you can check the reducibility of the polynomial just by trial and error, because here only finite number of elements are there, no? So only here 5 elements are there, 0, 1, 2, 3, 4. So you substitute the values one by one in the given polynomial. From that you have to identify whether the polynomial is reducible or not. First let me substitute x equal to 0. Then 0 plus 4 is 4. So non-zero value. So 0 is not a root of this polynomial. Next, substitute x equal to 1. So f of 1 equal to 1 plus 4 is 5. This is z5 of x, no? So 5 will become 0. Okay, so 1 is a root. From here itself you can conclude that f of x is reducible in z5 of x. Because reducible means the given polynomial can be written as product of factors whose degrees are less than the given polynomial, isn't it? So if only one root you can get, then you can directly write it is reducible. So but here I have checked for other numbers also. What about 2? 2 power 4. 2 power 4 is what? 16. 16 plus 4 is 20. Again it is 0 in z5. And then 3. 3 power 4 is 81. 81 plus 4 is 85. Again it is 0 in z5. And 4. 4 power 4 is what? 256. 256 plus 4 is 260. So again it is equal to 0 in z5. So 1, 2, 3, 4, all these 4 values are roots of this polynomial in z5 of x. Okay, but no need to proceed like this. Only when you find out one of the roots, it's enough, and directly you can say it is reducible. Okay, next one more polynomial, x cube plus 2x plus 3 in z5 of x. The same thing, you check with the number 0, 1, 2, 3, and if you get 0 somewhere, you stop there and you write it as reducible, otherwise you say it is irreducible. So f of 0 equal to 3, non-zero value. F of 1 equal to 1 plus 2 plus 3 is 6 equal to 6. But in z5 it is equal to 1, right? And f of 2 equal to 8 plus 4, 12, 12 plus 3 is 15, it's equal to 0. So here I am getting a 0. So here I stop here and I write it as f of x is reducible in z5 of x. Next one is f of x equal to x square plus 6x plus 12 in Q. We have to check over the field of rational numbers. See, this is a monic polynomial, isn't it? So monic polynomial means, here what can I do? This is a monic polynomial. What is the constant term? 12. So if there is any root for this polynomial in Q, it must divide 12. So what are the factors? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. So these are the possible roots for this polynomial. You have to substitute them one by one in this equation, and you have to check whether you are getting 0 or not. This is the procedure for using this result, but this is a quadratic equation only, no? So we can easily find out whether it is reducible in Q or not by using our regular formula. X equal to minus b plus or minus root of b square minus 4ac by 2a. Here this is an imaginary term, therefore this doesn't belong to Q. Therefore it is irreducible over Q. Just I have taken these two lines only to explain how to use this method. That is, see, this is 12, no? Find the divisors of 12 and you substitute them. Only these are the possible values which can be root for this polynomial. You substitute them, you will never get 0 with these values. So it is irreducible. Okay, right. Next one, f of x equal to x power 4 minus 22 x square plus 1. This is a monic polynomial, no? And constant term equal to 1. So the roots can be either plus 1 or minus 1, because the root should be a divisor for this one, right? So plus or minus 1. If I check with plus 1 and minus 1, both are not equal to 0. So f of x is irreducible over Q. Okay. Then next one is f of x equal to 8x cube plus 6x square minus 9x plus 24. Here I am going to make use of Einstein's criterion. look at these. For using Einstein criterion, leave the highest coefficient, look at the other things. These things are divisible by 3, prime number 3. So P divides 6, P divides minus 9, and P divides 24. But P does not divide this 8, and also P square is what? 9. 9 does not divide the constant term. So all the conditions for the Einstein's criterion are satisfied. Therefore f of x is irreducible over Q. Okay, next one. F of x equal to 2x power 10 minus 25x cube plus 10x square minus 30. So look at all these things. They have 5 as a common factor. 5 is the prime number, and it is a common factor for all these things, and 5 does not divide this 2, right? So now 5 divides 25, 5 divides 10, and 5 divides 30, and 5 square does not divide the constant term, and 5 does not divide this 2. Therefore by Einstein's criterion, f of x is irreducible over Q. Next one, f of x equal to 21x cube minus 3x square plus 2x plus 9. Here I cannot make use of Einstein's criterion, because here see, I don't have any divisors for the coefficients in this part, right? So Einstein's criterion cannot be used. I told you one more result, no, that is writing an equivalent polynomial in Zp of x, right? So I am going to write an equivalent polynomial in Z2 of x. So let f bar of x equal to, I am writing all the coefficients in Z2, right? For x cube, 21 means what? It will be in Z2, it will be 1, and 3 it will be 1, 2 it will be 0, so no x coefficient. Here 9 means it will be 1. So this is f bar of x in Z2 of x. In Z2 only two numbers are there, one is 0, another one is 1. You check f bar of 0 and f bar of 1. F bar of 0 is what? Plus 1, and f bar of 1 is 1 minus 1 plus 1 is equal to 1. So no zeros in Z2 of x. Therefore f bar of x is irreducible in Z2 of x. Therefore it is irreducible in Q. Here I told you, you have to be very cautious about using this result. First thing is, here this is a polynomial of degree 3, no? So here also you should get the same polynomial of degree 3. If the degree get reduced, you cannot use the result. When will it get reduced? See, this is 21, no? I am taking it as Z2. Suppose if you take Z3, then what will happen? This 21 will become 0x3. In that case, the degree of the polynomial will get reduced. So you cannot use the result in Z3 of x. This is one thing you have to keep in mind. Another one is, suppose it has a 0 in Z2 of x. Here I am not getting zeros, no? Suppose if in case on the other way you are getting zeros in Z2 of x, you cannot come to any conclusion. You have to take some other p value, that is either Z3. Z3 is not applicable, I already told you. So Z5 or Z7, any other prime number you have to take, and it will be more time consuming. If you are using this method, you restrict yourself to Z2, Z3. Okay, then you can easily find the result. Otherwise you don't go for this method, because it may be very time consuming. Okay, see, let's see one more problem. F of x equal to 9x cube minus 7x square plus 11x plus 5. Here also I can't use Einstein's criterion, right? I am not going to use the method which I have used for the previous problem. I will tell you why it is not applicable. Let me come to this directly. Suppose if I am writing f bar in Z2, how the polynomial will get reduced? This will be 1x cube minus 1x square plus 1x plus 1 in Z2 of x. Okay, in Z2 0 and 1 are there. If you put f bar of 1, it will be equal to what? 1 minus 1, 0, 1 plus 1 equal to 2, 2 equal to 0 in Z2 of x. So I am getting a 0 in Z2 of x. So this is not applicable. This result is applicable only when you get irreducible in Zp of x. Okay, right? So in Z2 of x it is not valid. What about Z3? If I write the polynomial in Z3, here 9x cube, no, so this will become 0x cube in Z3, right? The degree get reduced. So in Z3 also it is not applicable. Next prime number is 5. If you go for Z5, it may be difficult, or you may again get it as reducible. Okay, so I am not going to do this by this method. Instead of that, what I am going to do is, see here the constant term is 5 and the highest coefficient is 9. So look at the divisors for this 5. 1 and 5 are the divisors. Here 1, 3, 9 are the divisors. So what are all the possible roots for this equation? That is a0 by an you have to put. 1 by 1, 1, 1 by 3, sorry, 1 by 1 1, 5 by 1, next one 1 by 3, 5 by 3, next one 1 by 9, 5 by 9, that is a naught by an should come. You include plus or minus, so any one of these values will be a root for this equation. Okay, we have to check it by trial and error, no other method is available, so you check it by trial and error, right? So I find it that no that is no value from this set is a root for this f of x, therefore f of x is irreducible over q. Okay, next one, f of x equal to x cube minus 9x square plus 15x minus 2 over q. Here this is a monic polynomial, the constant term is minus 2, right? So the only possible roots can be plus or minus 1 or plus or minus 2. So if I check randomly, f of 2 equal to 0, therefore f of x is reducible over q. Okay, that's all. I hope you understand this video. Thank you for watching.